Hi, and welcome to this video in which I would like to brief you on uh, the first steps on using OpenMP, which is one of the famous libraries to implement shared memory parallelism. So the outline would go as follows. I would recall with you shared memory parallelism and multithreading in contrast with multiprocessing. Then I would talk to you about the fork join concurrency model, um, particularly the one that is used by OpenMP. And today in this video, I would just get you involved into the basics, the concept of private and shared values between threads, and eventually just a few first steps towards parallel for loops, which makes all the difference with respect to other libraries such as pthreads and what we saw so far with Java. So I have a very nice construct here, which is parallel for loops. Next time during the live session, we will dig deeper on those concepts and we will talk about the other special constructs that we can find in OpenMP. So let's start. First of all, just a recall for what we have said so far about parallel computing. So usually with serial processing, we have a serial code that goes sequentially line after the other, being executed on one runtime environment on one processing unit, okay, which is a single core within a single processor, okay. The processor for us being a CPU, and the core is one combination of arithmetic and logic unit, plus a control unit, plus all the necessary gates so that this unit is able to talk to the RAM, and fetch, decode, execute code from it, read from it, use its registers to store the data in it, and then apply instructions such as add, multiply, etc., etc. Okay, so this is for us a core. It's really one single processing unit that is able to process code sequentially. Even if sometimes we have loops and we have if conditions, so we have certain jump statements that would go back and forth in the code, but this is still called a sequential execution, and it's a serial code. Um, If you have a parallel architecture, your problem is not solved in this case. So it's true that you can use multiprocessing, which is already implemented by default in operating systems, so that the operating system will delegate to every single processor or core within a processor a certain different process, so that you can run 4 different programs in parallel. And then even the operating system usually uses the concept of multi-programming, which is the concept of actually keeping the processors busy. So while one of the processes, let's say process number I, is waiting on a certain input-output instruction, reading from the keyboard, waiting for a value to be entered from the keyboard, or waiting on a value to be read from the hard drive. Another processor another process, J, could get inside the CPU, arithmetic logic unit and control unit, to start execute on them, while the process number I is waiting for its input output to be done. So the OS can juggle between multiple cores, multiple processors, and can even juggle between 2 different processes over the same processor, and by doing a kind of a scheduling that you have already learned in the operating system course. Okay, but still on every single core, for every single process, we have a serial code, one single serial stream of instructions that are being executed one after the other. Okay, And here we are bound to the limitations of the algorithms complexity that we are designing. So if, for example, you want to search for a value within a certain array, then you have to do it sequentially, one value after the other, until you reach the end of the array, and then to really say at the end that the value exists or not. Okay, because the code is one single serial stream of instructions, and the for loop is really working sequentially, one iteration after the other. So it has to iterate over all the items in the array. So the question is, can we further parallelize these operations? And the idea is to use a parallel code, what we call nowadays a modern code. Okay, a modern code is a code that has been designed, particularly designed to benefit from parallel enabled architectures where we have multiple cores or multiple processors, CPU processing units within the same device or machine, so that we can split our streams of instructions into multiple independent, kind of like independent streams of instructions, so that we can execute them really in parallel without any interleaving or interlacing between their variables values and their execution sequence. So just to recall quickly the similarities and the differences between processes and the threads. So we have already talked about this in the part about Java multi-threading. So with multiprocessing, you create multiple processes using a fork and the routine, and eventually you can let one of the processes wait for the execution of the others using the wait routine. So you have explicit inter-process communication, and the synchronization is part of that communication. And the most important, let's say, context of execution of processes is that they have separate address spaces, so it's quite difficult to share variables between them. However, with the threads, it's just a kind of a um, fake task. It's not an effective process for the operating system. It will just see one single process with one PID, process ID, within which you will have multiple threads working in parallel, thread 1, thread 2, thread 3. So they can share the same memory space of the original process, so they can see all these variables, shared variables, although they can also define their own local variables here and there. So we can have the same variable name A in every thread, but having it initialized to different values, okay? But we can also have a certain shared variable S being initialized to 6 and being incremented by each of these threads once at a time. The final value of S can be guaranteed to be the total of all those values if we do the right synchronization between those threads. So synchronization must be done explicitly in the code so that two different threads won't access the same variable at the same time if it is shared. And this is how, by the way, they can do a communication through this shared address space. So it all depends on this basic fact. The same here, we need communication between the processes. Or I mean, the exact inverse is happening here because we have separate address spaces, so we need communication to synchronize them and to allow them to send and receive data between each other. Typically, threads are library defined, such as NP threads or Java threads, or as we are learning today with OpenMP. So just briefly, threads are easier to start to context switch, so to switch from one to the other, and to terminate. Okay, so this is why and they are typically cross-platform. So this is why we would often like to opt for the use of threads and not for processes. What about the data sharing issue? So do we always need to share data, or can we split data into chunks? Well, just to let you know that this is really problem dependent. So often it's problem dependent, and sometimes it's simply not feasible to split data into or to shard it actually into multiple chunks or shards. Rather, you have to share the data. But so one typical example of where you can safely split the the total amount of data that you want to process into two separate chunks and then work on them separately, then combine the final result, is what you usually do in image processing. So typically, if you want to apply, for example, a certain filter over this image, or you want to make a certain image recognition or image analysis on this image, so you can do it on you can cut the original image into two different chunks. You can partition your data into two different shards, and then give each partition to a separate processing unit, to a certain different process or a different thread. Allow each task to perform the calculation on that chunk, ideally using, of course, a different processing unit. And then you can combine the final result at the end after the processing is done. And then can actually use, if synchronization is needed, for example, to display or to save the final image in a single file, then these two different threads, they need to actually coordinate together. So they can use mutexes to give each other a certain signal when one of them finishes its work. Um, and this can be achieved actually between processes using message passing. So the same thing may be, or the same approach may be used when you are making certain simulations on in physics or in virtual reality environments, or for example in fluid dynamics. So the effect on a certain local zone can be analyzed by a separate process or a separate thread, instead of working on the whole object or environment. Sometimes this is not possible, and data must be treated at once, such as in particle transport simulation, or for example in machine learning. So maybe you need the whole space, data space, to perform a certain calculation, one single calculation, except that part of those calculations can be separately done and applied in parallel on the same part of the data. Okay. So to this end, no problem. You can, as I said, you can pass messages between processes if needed. If one of the processes loaded a certain chunk, or simply they can just share the intermediate calculations. But in this case, both of them, they can actually access the same data that is present on the storage, the auxiliary memory actually, okay? And similarly, between the threads, you can use mutexes to synchronize the access to this shared resource. No problem, but most probably you will allocate it only once. So a big advantage of the multi-threading approach is that the whole data that should be present in the memory during the calculation is not duplicated twice in the RAM into each of the separate private memory spaces of each process. Rather, you can load it only once and allow each thread to work on it, to work on a different chunk of it. So in this case, this is really useful. Okay, and in the previous approach, there are no there is no edge for the process-based approach over the thread. Both of them, they can achieve the same thing. So this is why when you have a shared data that is loaded only once in the memory, and that both threads can share and work on at the same time, this would be really convenient. And again, once again, if at any moment they need to coordinate their work, they can use, whether it's in this case or in that case, they can use mutexes to do this coordination. So before digging deeper over OpenMP, so we have already seen Java multithreading because you're more familiar with it. It's based on Java and it's cross-platform. So this is what is nice with it. We didn't learn in depth about the concurrency package, but already what we have been offered with multithreading to make a fork join approach and to synchronize the threads was really enjoyable. It was quite easy, high level, and we didn't have to take care of the details. Know that there are plenty of other approaches. One that we will learn later on that is based on POSIX threads, P threads. It allows also for a basic fork join model and to do synchronization. Yet it's a little bit verbose. It's available on the C++, Fortran, and typically under Linux, although there are certain libraries that can simulate P threads under Windows. But mainly they are designed to be efficiently run on Linux machines. And there is another library that is also available for C, C++, Fortran, and on Linux, Windows, and other distributions. So this one, actually, you will see that it's much more elaborate than both pthreads and Java multithreading, because it uses very simple directives that can be passed by the compilers, by the C compiler, and it would understand that certain zones should be parallelized into separate tasks. We can parallelize loops. We can use reductions, make load balancing, and control plenty of other parameters of the parallelization process. Okay. In addition, we can also use other forms of parallelism that we will talk about later on. So it's really nice, and we will see the first steps, the basics of OpenMP in this deck of slides. So what is OpenMP? It's the open multiprocessing specification of shared memory parallelism. It's a computing-oriented framework for shared memory programming. As I said, it uses the threads to execute streams of instructions that share memory address spaces, and it distributes threads across CPU cores whenever it's possible for parallel speed up. Okay, so to really execute those streams of instructions in parallel whenever it is possible. So let's consider the first example about OpenMP. Our hello world program or example about the OpenMP is the following. So it's a simple C program in which we have included the standard input-output. I think you can change this library according to your machine. Maybe standard input-output alone works for you, or the conio. So it depends on the input-output instructions that you are planning to use. But the most important part is this addition here. So you should include the OMP.h library in your code to be able to use the OMP directives, the OMP functions, and the OMP predefined routines. So the first routine that we are using here is OMP get max threads. Okay, so this function would return, it's executed by one thread. Sorry, before starting a parallel zone, the code that you write is a code, normal code that will be executed only by one thread, which is typically the main, let's call it the main thread. Okay. Whenever you have a pragma OMP parallel, what this declared that you have a parallel section or a parallel zone of code. So you can use braces to delimit this zone. And actually, this code is executed in parallel by multiple threads. But the question is, how many threads? How many threads will execute your code? So actually, you can define the number of threads on the command line. We will get back to the command line in a few seconds, but just imagine here that you are defining a global variable, environment variable, OMP num threads that you are setting to 5. You could set it to any other number that you like. So this is one remark. You can set the number of threads outside of the code, and you can get it, you can read it, okay, using this instruction here. What is the maximum number of threads? And then you can say here that OpenMP is running with that number of threads. So after setting this variable to 5, you can see here when we are running our code, it's giving us OMP with 5 threads. Okay, so it means that there are really behind the scenes 5 different threads executing the code. Okay, not for those lines again, but only when you open this pragma OMP parallel. So this leads us to this directive. Again, everything that you start with a pound with a hashtag, it's a compiler directive, such as hashtag include or hashtag define. Okay, so here we have hashtag pragma OMP parallel. Okay, so also this directive wouldn't work unless you have this OMPH, OMP.h import or include. Okay, so you have to refer to this library OpenMP, otherwise your code won't recognize these directives. The nice thing with directives is that they do not alter the behavior of your code as long as you don't have the library or as long as you don't have multiple cores. Your code will work exactly as if it was sequential. But just when you have the library and it is able to use multiple hardware cores, then in this case, the code will be really parallelized. So this makes your code non-intrusive and optionally benefit from parallelism whenever it's available. Okay, otherwise it will fall back to serial to become a serial code once again. And this won't alter the semantic of your program or what your program is doing. So within this parallel zone, we are just printing a message, hello world, from the thread, and we're using this routine to say OMP get thread number. Okay, so this routine, as the name says, it returns the ID of the thread that is being run. And the IDs actually of the threads will range from 0 to n-1 when you have n different threads, okay? So 0 being the main thread, okay? And the others being numbered from 1 up to n-1. So let's look at the command line. If this file is saved into this file here, hello underscore omp.c or .cc or cpp, then the command gcc on Linux with this option -f-openmp would be able to compile the code even if it has this include and those directives. Okay, so you have to add this option -f-openmp. And then you can choose, as usual, an output file that you can execute with this command / the name of your output file because it's a binary file. When you run it, as we said, the first line will be displayed from the main thread only once, and it will display the number of threads. However, this line that was written inside this parallel zone, it will be executed by each one of the threads. How to designate each thread? Well, you know it already. You use this OMP get thread number to be able to assign a different task or a different job to each thread. Okay, so we'll see how we can use um, this in the SQL to assign particular jobs to different threads. Please note once again that OMP number of threads controls the number of OpenMP threads, which is by default the logical CPU count that you have on your machine. Otherwise, you can also increase it, and then a context switching will be done to juggle between the multiple threads. So how this code really worked actually. So the OpenMP library implements the fork join task model, where we believe that we have a master thread that forks into multiple child threads, okay, to perform a certain task in parallel, okay, concurrently, and then once they finish, as if we have a brace. So do you see here the braces that we have here? So this is end of the parallel execution. Okay, so it's kind of an implicit barrier. Okay, so we have here a certain implicit barrier of the fork. Okay, that we did at here. So as if we have a certain fork here and a certain join at this place. Okay, and the code goes indefinitely as so. So every time you need to achieve a certain part of your code in parallel, you fork, you declare a certain parallel zone, and then when it's done, when you have the closing braces, then those threads will join back again, and then the master thread will wait for them to finish their execution, and then will take the relay and will continue working on the subsequent tasks. So this is quite useful, quite recurrent in parallel programming, because so often you need to do certain initialization over, for example, a certain array of values or shared variables, and then you will ask each thread to work on a certain chunk of your data, and then you will get their intermediate results, and then you update your shared data, and then you ask them to post-process your data once again, and so on and so forth. Okay, so this happens so often, and it's one of the most used models in designing parallel programs. Let's consider another example. So here in this example, it's quite similar. We have just a main. We have a pragma OMP parallel with this OMP.h. So most probably you will be using this studio.h on your computer. And then as you see here, you will be forking the threads, and here you will be joining back again. And here we are doing the same thing. We are displaying the thread number, and this will be done by each thread separately. And then when we print done, okay, so we could also print something like a start at the beginning. So if we do printf start at the beginning, you will see that start will be only displayed once, okay, and done will be only displayed once. But all the code that we have here, it will be displayed n times by the n threads that we have. So most probably, if you check here, you would notice that the number of threads was equal to 4, because by default the logical number of the number of logical CPU units was equal to 4. But after tweaking this parameter, or maybe because this parameter was set to 4 also, okay, so we don't know, but by default it would be equal to the number of logical CPU units. If it has been set by hand to 8, then in this case you would see that we have 8 different executions of this instruction, and then the done being displayed at the end only once after this join. So this proves that actually this close braces, it's really a join moment in the lifespan of your code. Please also notice that the threads does not execute in the right order. So here we have
complete different order. Okay, so also we have a different order each time we run our code, which is really good. We have to live with it. We have to benefit from it, by the way. Okay, so each thread progresses, makes its own progress independently of the others, and whenever it happens that it finishes its work, it can yield its final result, no problem. Okay, but given these join moments, those close the braces, we can always count on them to make sure that all the threads finished a certain task before doing something based on their intermediate results. So how do we control the variables? What are the global variables, shared variables, and what are the private variables? Because we have said at the beginning that threads would share variables in the shared memory space that belongs to their corresponding process. So there are two different methods. You can define your variables outside of the Pragma OMP parallel zone, okay, on condition that you specify using the private and the shared uh, um, uh, commands. You can define which variables you would like to maintain privately accessible, and hence privately, separately changeable by each thread, and which variables you would like to have them shared. So if you define A as private, then each thread would have its own copy of A, okay? And for example, if you put in A, OMP get, just let me check, so thread number, yeah, because we have another one, which is the number of threads, okay? So don't forget, you have another function, OMP get max threads, which returns the total number of threads. So okay, so if I get the thread num, okay, and I put it in A, so this variable won't be overloaded. Okay, you can safely display it here. You can say printf A, and then the variable would be fine. You can have really separate values. What I mean by this is that even if on this line the first thread has been paused, and then another thread would reach this line of code to put something else in this variable A, well, it's not a big deal because it's another copy. Okay, so each thread, if you look at each thread, thread one, let's say, and thread two, so each thread has its own copy of A. So this one puts in it the value one for the ID of the thread, and this one, and before displaying it on the screen, output A. It's not a big deal if this one reaches this instruction here and then execute assigned to A2, because this A is really a different variable in the memory, okay? However, this is not the case for B, okay? So if you use B to store the thread, even if you call the OMP get thread number from within this block where each thread will save a different value in it, if you display B, in this case, maybe you will have the same ID displayed twice. So maybe you will have I'm thread number 0, I'm thread number 2, and I'm thread number 2, even if you have 3 threads available. Where is the thread number 1? So maybe if you thread number 1 stored the value 1 in the variable B, maybe it has been paused, okay, so it could not display right away. Then thread 2 came, stored 2 in the variable B, which is shared, and then displayed the value of the variable B on the screen. When the sequel of execution gets back to the thread number 1 to display the value of B, it would have find it equal to 2 in this case, okay? It would find it equal to 2 in this case and not equal to 1, because thread number 2 would have changed it meanwhile, okay? So do you see? But if you use the variable A, which is private, so no problem, each thread would have its own copy of the variable A, and it would work on it locally. So you can also imagine that private, it means local to the thread, okay? And that the shared variables, they are global sorry, global for all the threads. Okay, they all of them see it at the same time. So another way is to use scoping. So please note that all the values that you define outside, they are declared by default as shared, and all the values that you declare inside, they are safely assumed to be private, okay, by default, and hence each thread would create its own copy of that variable A. Okay, this is quite intuitive. This is quite normal as a default behavior, but please know that you can change it with these constructs and after defining all your variables outside of this block. Okay, so now I think we can summarize what you learned so far. You learned that you can use this directive to create parallel zone. You can use this instruction OMP get max threads to get the total number of threads that you can set on the command line. You can run your OpenMP code by adding this option to the GCC command, as long as you are using omp.h inside your includes. And then you can use OMP underscore get underscore thread underscore number to get the ID of your thread. And this yields 0 outside of this block because it represents the main thread that has ID 0 by convention, by default. But inside the pragma OMP parallel, it returns the corresponding the ID that corresponds to every single different thread, and the order does not really matter here. When you open these braces as if you were forking over the threads, and then when you close the braces, it's like when you are joining the main thread once again. When it's like when you call join from the main thread in Java, let's say. So to see this in action, we have considered another example where this message done is systematically displayed at the end. And we have also seen that changing the number of threads would alter the results, but once again, we don't have any guarantee over the order. To avoid having any problems with the values of the variables, you should know that all the values that are declared outside of the pragma OMP parallel scope, they are by default shared. Nevertheless, you can also determine their scope by using the private and shared directives, okay? Of course, if you have more than one variable, then you can separate their names by commas, okay? So again, otherwise, only the local variables that are defined within the fork section will be considered private. Okay. One last example about the strength of OpenMP is the example of making parallel for loops. So imagine that you have a for loop that would iterate over the elements of a certain array. So here maybe we have 10 different iterations. So the serial code would have done iteration number 0, 1, number 2 and 3, 4 and 5, 6 and 7, 8 and 9, and then 10 and 11. Okay, so all in all, we have 12 different iterations. So as you may see, if you have 4 different threads, so you can achieve this code in 3 iterations actually. How? Well, according to this diagram, it seems that the first time, the first, let's say, sequel of execution, each one of these threads has taken into account 2 of these iterations. So thread number 0 start working on the iteration 0 and 1. Thread number 1 started working on 2 and 3. Thread number 2 start working on 4 and 5, and then thread number 3 started working on iteration 6 and 7. If you check the indices, you would see that each thread number I has worked over over the iterations 2i and 2i plus 1. Okay, so over 2i, and then the next iteration that was considered is 2i plus 1. You can always find such correlations easily by analyzing the indices of the threads and the indices of the iterations. And then at the second time, only 4 different iterations were left. So this is why the first thread, number 0, took in charge the iteration number 8. This one took 9 in charge. Thread number 2 took iteration number 10, and this one iteration number 11. Okay, well, this is just a sample way of execution. So all in all, if you check, each one of these thread would have done, so thread number 0 would have done 0 and 1, 2 and 3 here, 4 and 5, and then 6 and 7. All in all, each one of these threads would have made only 3 iterations, okay, and not 12 iterations like before. So if you check the there will be a quite interesting speed up at the end, because ideally, like within only 3 iterations, all the 12 iterations would have been solved so far. Okay, so it takes only 3 cycles of time kind of to perform those iterations instead of doing them so instead of doing them sequentially over 12 different iterations. So clearly it's very appealing as a gain or speed up, okay, a gain in speed. Nevertheless, there are plenty of details to be taken care of before assuming this excellent rate of enhancement. So the basic idea is that we can simultaneously launch multiple threads to work on separate iterations. So there is a scheduler that would assign loop iterations to threads, and then each thread processes 1 iteration at a time. Okay. Of course, so because each thread would work on a separate core or processing unit, so it would be able to work on 1 single iteration at a time, except that we would have assigned to it a subset of those iterations. So the question is how usually the iterations would be assigned. So is it always something like this? Okay, well, you will see that this is a particular case based on a certain type of schedulers and a certain type of configuration of that scheduler to work on chunks of 2 by default. Okay, and when it has been left with only 4 different values, it distributed them one by one over the threads. So how the values are distributed, it really depends on the scheduler. We will see it most probably on the next live together. So the OpenMP library will distribute the iterations of the loop following the Pragma OMP parallel 4 across the threads. Okay, how this would work, let's take an example. If you have this for loop going from 0 to n, if we print f that the iteration number I has been processed by the thread number OMP get thread number, then you will see that it really depends on the used scheduler of the OpenMP. You will have different possible distributions, okay? But if you are fixing the scheduler or the configuration of the scheduler, then you will see the same number of iterations being assigned to the same thread systematically, okay? Yeah, so let's see. So grosso modo, the iterations will be distributed across the available threads, but how this is done exactly, well, this depends on what we call the scheduler, as we shall see in a few slides and typically on the next session. So within Pragma OMP parallel, we can create a Pragma OMP 4, okay? So we could write Pragma OMP parallel 4 right away and just write our for loop. use the braces here, close it there, and then the whole for loop would be parallelized, okay? But we can also use a pragma OMP parallel and then put inside it a pragma OMP4. So the code placed here will be executed by all the threads. Alternatively, it's an alternative way to specify private variables to declare them in the scope of pragma OMP parallel. Okay, so for example, if you want a private number equal to 0, okay, that will be separately used by each thread, we can use this scope here, OMP parallel scope, and then write the pragma for at this stage. Okay, so when you write pragma OMP4, this for loop, it won't be wholly executed by all the threads. No, chunks of it actually, because it's a pragma OMP4, iterations will be as before distributed across the available threads. Okay. However, the code that you will have outside of this block, of this block, it will be executed by all the threads. Okay. So if you, for example, if you put here at this stage or before this block, if you put a certain for loop, normal for loop, I equals 0 up to whatever you want, let's say 10, I plus plus. If you display hello, if you print hello, then hello will be displayed 10 times by every single thread, okay? Because you haven't added before this for the hashtag pragma OMP4, okay? If you don't add it, then it will be executed by all the threads. And this means that each thread will be display the word hello 10 times. Say you have 4 threads, then in total hello will be displayed 40 times. Okay, but if you add this pragma OMP parallel as we have done here, then all in all, no matter what the number of threads that you have, whether they are 4, 8, 3, 5, 10, 20, anyway, all in all, there is a guarantee that only 10 times this word hello will be printed, and simply the total number of 10 iterations will be distributed across the available threads. Okay, so please think about these examples. Ideally, try them out on your machine, and then let's discuss the next time during the live how the loop scheduling would work in OpenMP. So we have static scheduling, dynamic scheduling, and guided scheduling. And for each one of them, we can either be satisfied with the default chunk, or we can specify our own chunk of assignment for the multiple threads. Okay, so more about these and then live session, next live session on a Friday. Okay, I would suggest to work on the lab also. So please check the lab exercises. They the first couple of exercises, they must be feasible because they discuss quite similar exercises for now. And if we jump to the last slide, you will be able actually to find over those links that redirect you to the LLNL famous page for the documentation of OpenMP. You can already read about the parallel and for directives and about all the environment variables and the OMP functions that we have talked about today. Okay, so more about those functions later on in the next sessions. Thank you so much for your attention and see you during the live session.